Alright guys, what's up? I'm gonna do another video today. So, lately I've been doing a lot of E&M. So we're gonna do some E&M. So I got this problem ready for us tonight. I'm gonna do a nice little problem. I got this one from the master, Jin Au Kong. So what's the problem? Well, it's very simple in theory. We have an interface that's a conductor, right? We got a conducting interface. And then we have this kind of realm D. Here we have a dielectric and we have non-magnetic material. And then here we actually have free space. And the question is what modes support this conductor, or this kind of idea. So this is taken from Jin Au Kong, and we're going to solve this today. So I'm going to quote a bunch of stuff from Zhang, but the main ideas are going to be this. We need to find the modes along this conductor. So let's set up our coordinate system. We're going to have Z in this direction, and then we're going to have X in this direction, and then so that means that in this case Y is over there. Doesn't really matter, as we're going to see that it's only going to depend on X. Since the problem is symmetric in this ZY plane, no problem. So let's kind of attack this. So we want to see what modes support this waveguide. We know that if we have a conductor, then any surface is going to reflect off of that, because in the conductor we must have that the electric field is 0. So that means that all plane waves that hit this surface bounce off. And then on this surface here, we're going to have a reflection and transmission coefficient that we can kind of find using our solutions of the Maxwell equations. So starting off with Maxwell's equations, we can derive this kind of from scratch, which I'm sure you guys want to see. The main result is that, using the following equations, that we have Faraday's law, and we can also use Ampere's law. So we use these two laws, and then the way you do it is you can take the curl of either of these again, and the main result is you get an equation in the form of this. And so I'll get into it. We essentially get the gradient c squared d squared t squared times this vector, which is either the electric or the magnetic fields. And so this is known as the Helmholtz equation. And so most people, when they write this, they actually don't write this column vector because it's kind of too much. We just can abbreviate it as psi, and we know we need to just be careful of what we're talking about. So when we're talking about plane waves, we take the plane waves will always take the form psi equals some transverse component times the propagation. So we can just do I, and then we can just do kz omega kz z minus omega t. So we got this propagation in space along z, and then we got a movement in time. So this is like a wave traveling along the z direction. And then this will be the transverse components that we have to find. So let's do it. So we're going to do the TM modes first, and I'll explain why once we get there. So in the TM modes, the main result, I'll just put some light here so you guys can see it. Oh yeah. Let me get the tea bags here. Fire. Alright. So TM modes, we have that the magnetic field is fully transverse. Transverse magnetic, that means that Hz along This is 0. So that means that the only propagating field is going to be the E field. So we can set up our equation here. So del squared transverse, or actually we'll do the full one. We'll fully derive it. Minus 1 over c squared d over dt squared squared. Ez times e to the minus I kzz minus omega t is equal to 0. That's the Helmholtz equation. Then we're going to take the derivative. So here's where this is interesting. Kz is, sorry, epsilon, or Ez, we call E equals this times the time component. This is symmetric in Z and Y. So if I choose Z or Y here, it needs to be the same. So there is going to be an orthogonal propagation, or there's going to be some rotational basis where this here and some linear combination with y is equal to just picking one of the axes. So I essentially will use that result to say this is only a function of x, the non-symmetric component. So what that does is you actually get the following. You get this, so you get dx squared, and then dy dz. dz will act on this, and dy will be 0. So you get plus minus I kz squared, and then you do the time derivative, minus 1 over c squared omega t, so minus I minus plus times I omega squared. And that's all going to be multiplied by epsilon z times this I kz minus omega t equals to 0. Okay, so what do we see? We see the following. We get dx squared minus kz squared, and then minus plus omega over c squared epsilon z, and then this cancels out with 0. So we got this this little ODE here. Okay. So this is actually quite easy. We can define we can look at this here. We can say that this is kr. Kr is going to equal to omega over c and times n. So in this package here, what's changing is that c is different in different materials. There is going to be a hidden n here that we need to be wary of, and so we can say that kr is omega c, I believe, over n. So let's just do the ideas here. So n is defined as I don't actually remember. We have to double check that here. So let me just quickly do index of refraction. Yeah, so I was right. So the index of refraction is defined as c divided by the volume of the thing you're in. So here, if c is actually the material, like if c tilde is the material in the dielectric, it's going to be defined as c over the index of refraction. So k is defined as omega over c or v. Like it's defined as omega over v in the material, and if it's monochromatic, you get c times n. So we can just call this thing the k in the region, and so essentially what we get is we get dx squared plus k region squared minus kz squared, and this is what Jin Au Kong does in his book Theory of Electromagnetic Waves. So we get this, okay? And then we can define this quantity, and I'm going to use Zhang-Wo's notation here, as squared of the region you were in. So, yeah. So essentially what we're left with is the Helmholtz equation in one dimension plus squared epsilon z. Okay. Okay, we've derived the field equation for the TM wave, so now we're going to solve it. So I'll just talk here. So let's just inspect this drawing. So for guided waves, let's look at different values of omega r. So when omega r is equal to k material squared minus kz squared, or kx, z. And so this is actually equal to, like, the k vector in a material has to be equal to the z component plus, in this case, the x component, because you have to sum up all the components, and it's just Pythagoras theorem. There's one along z, and there's going to be one along x, and so the full wave vector is just going to be Pythagoras theorem. So these two quantities, this one and this one, are actually identical. And so what is conserved? This is conserved, and this is conserved, because your propagation will not change. It needs to be like there are boundary conditions on the tangential components along, or of the tangential components along the electric field. And that's why we picked the TM modes first, because we can just simply say that, okay, we need the electric field to be tangentially continuous, and where does k fit into that? The pointing vector. So we're going to have energy conservation. So we're just going to set that this and this are actually conserved. So this actually sets a boundary on what modes we can have. So let's talk about that. So first, we're just going to look at the different regions. So suppose that this dielectric is bigger than space. So this is bigger than this. Well, k naught is then going to be less than kr squared, right? That's an exercise for the reader. It's not too difficult to figure out why. What that means is, for our wave to be guided, we need to have an oscillatory wave in the material, and then we need the wave to decay outside. This means that outside we need to have k naught squared less than k z squared, and inside we need that kz squared is less than kr squared, or in this case k core. We can call it k core, right? So we need the oscillatory here, and then the evidence in here. That'll make sure that the wave propagation is guided along this direction, not losing any energy. That's the whole idea. We can't lose energy. So with that in mind, we can actually start to attack our problem. So we know that we have these two conditions, and we have this equation. So that allows us to actually find all the solutions. So I'll just write them down quite simply. So for this, so we'll first do the core. So we can call these three regions. 1 is the conductor, 2 is the dielectric, and 3 is the the air. And we'll redraw that here just so we don't forget. 1, 2, 3. So this is air, and then epsilon, this is a conductor. So E is 0. Okay, so this here times our electric field, Z, 0. So this has easy solutions. So in region 1, E is equal to 0. So this is equal to 0. Simple. In region 2, we're going to have, we need to have dx, or dx squared plus core squared, epsilon z equals 0. Epsilon core is equal to kr squared minus kz squared. We need to have the condition that kz less than kr. So that means this will be positive, and then so we get that epsilon z is equal to e to the or a I gamma c x plus b e minus I gamma c x, and that's just the same thing as saying a like it's not the same A, but I don't care. Gamma Cx plus B sine gamma Cx. Okay. And then in region 3, we have the same style solution. I'll just write it down because it's just the same thing, but instead of gamma C, it's gamma O, or air. And it's just going to be not imaginary. So we get A e to the gamma OX plus, I should call these B and C, or D and C, e to the minus gamma OX. And so, okay, so this is our solution, so we'll apply the boundary condition. We need at Ez of 0, 0, because that's the conductor. And then Ez of infinity is equal to 0, and that's because decay slash, yeah, it's just a decay. So, damn, so, okay, we got Ez, so, no problem. Here, we need to have E of 0 to be 0, so that means that A is 0, so we'll just call this B sine gamma Cx. And then 3, we just get this one, C equals 0. And so we have the full solution, basically. We get that, I'll just write 2 and 3. B sine gamma Cx d e to minus gamma naught x. And then there's obviously a time component, but we only are looking at the prefactor, so it's not really that interesting. And in principle, we're going to have a sum over all of these modes as our true solution. So I've only kind of picked one out here, but in principle, it'd be a sum. So we need to do some matching here. So now we're going to match the conditions. And so the main thing is that we can recall our ideas from Maxwell's equation, and so we get that z, or we have x in this direction, so x cross E2 minus E1 is equal to 0. This is from the match boundary conditions on dielectric systems. So we're going to have the x cross y, that's going to be minus y hat, but it doesn't matter because it's 0. And this is at x equals d. So we get b sine gamma c d. Oh, and this should be actually minus d. Sorry, okay, why is this minus d? Because it needs to be shifted. Because the field starts here, right? So we can't miss that. So that was a mistake, but we got it fixed. So update, new update. Okay, and this equals to d, because this is 1. Okay, so we get, or minus equals 0. So we just get that d is equal to b sine gamma c times d, or we get the full solution that epsilon 3 is equal to b sine gamma c d e to minus gamma naught x minus d. Okay, and then epsilon 2z is equal to just b sine gamma cx. And so we can define b as the amplitude of our initial wave. Okay, so that's the first component. So now we can just get the other one. And so here I'm just going to quote the result from Zhang. Well, I'll pull it up here so you guys can indulge. The main idea is going to be that we can essentially use the results of Maxwell's equations just to find the other mode. So I'll pull it up, I'll write it down. it's kind of simple in this case. We're going to get that the tangential components are just going to be equal to I kz over gamma region squared times the gradient in the transverse direction. So in our case, we get that E3 is going to equal to x hat b sine gamma CD minus gamma naught x E minus gamma naught x minus D. And then in the dielectric, we're going to get just the cosine. Okay. Yeah, that looks good. Oops. And the H components of this are also pretty simple. I'll just write them down here. H components are just going to be in the transverse direction, and they're going to be omega epsilon region over, oh my gosh, I forgot to put in the I kz over omega region. So in this case, omega naught squared, and in this case, omega c squared. Okay, we should probably write that down one more time. I'm just going to edit this here. So, okay, so that becomes I kz over omega c, and then here we get I kz over omega naught. Yeah, that looks good. There you go. We fixed it. Okay, that's the vibe. Lastly, we get the transverse components. This is equal to omega epsilon region over kz times the cross product of this with the tangential components. And so that gives us H2 and H3. All we got to do is take the cross product and multiply. So in 2's case, we get z cross x is y hat, so we just get a y component. And we get, man, what do we get? We get minus I omega epsilon r over omega c b cos gamma c x. And then in 3's case, we just get I omega epsilon naught over, and this is c over gamma naught times b sine gamma cd e to minus gamma naught x minus d. Okay, nice and simple. Honestly, it's not a big deal, but we need to know all these. Okay, good. The cards are on the table. So now we just need to match the boundary conditions to find the other relation. So I'm going to just do this, and I'll teach you guys how to do it. So really simple. What do these things need to obey such that they are usable as TM modes? Well, we've already kind of hinted they need to match the boundary conditions. So in this case, there's no really easy way to do it, but essentially we've already done like one of them. So we know that this has to satisfy here. This has to be satisfied, which implies that this is just Gauss's law, low key. So the other ones we can have are going to be matching the surface charge, the surface current, and the fact that it can't be a monopole. So I'm just going to abuse the fact that that there is no surface current. Can I do that? Well, I know for a fact that this is automatically satisfied because we only have y components of h. So that's not going to really help us all that much. We can use the fact that there might be a surface charge. Let's think about it. So the surface charge comes from a free surface charge density. In this case, we don't have any surface charge because we don't, like, there's a conductor, which should imply that there's surface charge on that surface, but between the dielectric and the air, I don't know. I don't think there should be any surface charge. Anything that's free. So there should be no free charge. It should be all induced. So we can just say that x dot d2 minus d1 is equal to the free surface charge. Okay, so the free charge, in this case, that's equal to 0 because there's no free charge. So we're going to do at x equals d. So what do we get? We get, we just get these relations here. So we get, so b sine gamma c d ik z over epsilon naught. Oh, gamma naught. Shoot, gamma naught times epsilon 0 minus, in this case will be plus b cos gamma naught d ikz over gamma c equals 0. Okay, we get this relation here, and there's a sneaky little epsilon c in there that I forgot. So this cancels out with this, no problem, easy peasy. We get, let me just check if I didn't miss a minus sign here. There should be a minus sign here because we take the derivative, you get, yeah, there should be a minus sign from this. Yeah, plus. Okay, so we just essentially get that b cancels out, and you get sine gamma cd over cos gamma cd, right, equals gamma naught over gamma core times epsilon. So it's flipped, so it's epsilon naught over epsilon core. Or tan gamma cd is equal to gamma naught over gamma c, epsilon c over epsilon 0. Okay, and then what's next? Well, this is actually quite good because this gives us a dispersion relation. So first things first, what the hell is up with this? Well, we know that gamma c squared is equal to kc squared minus kz squared, and this squared is equal to k naught squared minus kz squared. So in reality, we can actually kind of play around here. The main thing to note is what's going to be positive and what's going to be negative, right? So we know that omega naught is always going to be negative here. So we can, like, this is going to be negative because it's evanescent, which means that there's a decay. So what we can do is we can actually just reparameterize this in terms of W, or we'll just call them kx2 and then kx3, right? And that gives us a really nice dispersion relation. And so essentially what you do is you flip the sign of these two here, and then what you get is that if you flip the sign, you can add them together and you get that kx squared plus k. Oh, this is kind of complicated. Okay, we're gonna redo it. So we're gonna say that we're just gonna flip this sign. This has omega mu naught epsilon core. That's secretly what this is. So this and this will cancel. If you add them, you get omega naught squared plus omega c squared is equal to omega mu naught. And here's the kicker. We get omega c squared plus omega naught squared. That's the detail. So that's the detail. So let's zoom in on the detail. And so what this defines is a circle. Here, tangent, simple. Essentially, you get this transcendental equation that this here has to equal to that. So if you just like to be honest, I've kind of overcomplicated this, but the main idea is this: that if we put omega c on this axis, or omega naught on this axis, omega c on this axis, then you'll see that this form is just tangent. So nothing too complicated there. And 1 over c, like you'll get like a relation like this. But in reality, it's like this because of this conservation. So this is kind of like, this needs to be equated to this, but in reality, you just get this curve. And so you actually get modes that can exist. So these are the TM modes, are solutions to this transcendental equation. Okay, that's what I wanted to show. So let's quickly review. So for TM modes, we state this fact here. We get the solutions of these guys. Just get the solutions just by solving the Helmholtz equation, so nothing too like complicated, just you solve Maxwell's equations. And we get boundary conditions from the fact that there's a conductor here and there's air here. You do this, and then you get the dispersion relation, which is there. You can do the TE modes as well. And so to get the TE modes, there's actually a relation in what do you call it, in Zangwill that's quite useful. So suppose that you do have the TM modes. You can use the impedance of the material to solve for the other guys. So I wrote T, but I meant H. So in this case, HTE is just equal to ETE times Z. And ETE is equal to the simple fact minus Z HTM. So let's see if we can just kind of do our analysis here and just solve for the dispersion relation in TE, because we kind of have everything. So in TE, we still need this thingy to occur. We need this boundary condition to occur. So we can say that x dot by dte delta is equal to 0. And so that actually implies that h ETE. Yeah. So HTM minus Z has to be. So we can do. So the minus Z will be so Z. Okay. So we can do. This will be 0 actually. So that's a bad example. We can use the other one. So in this case, we can use the surface current. Because x dot delta, I think that should still be 0. Okay, hold on. So we need to low-key lock in here. Okay, lock in activated. We're gonna have the following problem. We need to have x. So this is going to be in x and in z, and then this here is just going to be in y. That makes sense. So we want to look at b. So x dot this. That should be 0. Yeah. So x dot z core ETM core minus Z naught ETM naught equals 0. So what is TME? That's just this here. So we just get the exact same thing with Z. So we get ZC minus B cos gamma C D IKZ over gamma C. And then plus Z naught B sine gamma CD IKZ over gamma naught. Okay, well, we get the same cancellations is equals 0. And you actually get like the same thing. Basically, you get gamma C over gamma naught. And then this time, you get Z naught over ZC. And so you can see that the dispersion relation is very similar, just we can do it in terms of this impedance factor there. And the impedance factor, it's, I believe, just need to double check impedance of free space. I believe it is, yeah, Z naught is equal to 1 over mu 0 over epsilon 0. And you can change it because this is equal to 1 over epsilon naught times c. And we know that 1 over epsilon times c is just equal to 1 over epsilon naught. Aha! C is going to be nothing but, like c, like in like a slow version, it's going to be c to over n. N is going to be known. N is, man, what is N? N is the refractive index, but what is it equal to? I think it's the ratios of the dielectrics, I hope. Yeah. Yeah, so this is kind of actually non-trivial, but the idea is that n here is actually root epsilon refract, mu refract, in this case is this. C is, or I'll just do this again. So this is equal to root material mu 0 divided by epsilon mu 0 times 1 over root epsilon naught mu naught. Man, what do we get? We get this crazy expression. We get in material ZC is equal to this root epsilon r over root epsilon naught. Yeah, that looks okay. Yeah, I mean that's looks like yeah, I mean I guess so. Whatever, it doesn't really matter. You get another one like this. So in this system, the system can support both TE and TM modes. This looks like the right answer to me. So TM. So we get both of them. Yeah. We can ask, does this support TEM modes? Well, this one's really easy actually. We can do this as well. So we have a conductor, an air in this. We can actually just solve Laplace equations. So in this case, we just assume is Ez equals 0 and Hz equals 0. Well, if you set both of them to 0, we can essentially say that the field has to be 0 at the conductor. And so just solving Laplace's equation for a potential, there's no charge anywhere. So the only solution that you can get is like the form AX plus D. But since it has to be 0 at infinity, this implies that A is equal to 0. So B is equal to, or like the potential is equal to a constant at most, right? So if the potential is a constant, what do we have, right? So if the potential is a constant, the best field that we can get is going to be the gradient of a constant, which is equal to 0. So no TEM modes. So yeah, anyway, that's kind of the vibe. So what do we solve? So this is a problem from Jin Au Kong. Go check out his book. I think he died, but his book lives on. So, actually, did Jin Au Kong die? His book's really good. I really hope he's alive. No, he passed away. Yeah, so too bad. He was a really good scientist and engineer, and he passed. So yeah, I mean, go check out his book. I hope you guys like this video. Bye.